Good afternoon, everybody. I hope everyone's having a wonderful day. So today, before I get started, I just want to mention two things. First, I will be posting the exam format around Friday. So like the midterm, I give you a format. I'll be doing the same thing for the final exam. It'll be rather detailed, and it will provide you a lot of details that'll help you prepare for the final. Just like when I talked about the midterm, and you know how I told you about the written problems, what the written problems were going to be about, this exam format will tell you all about these things as well. So, that being said, one other thing, I will mention this some point, probably next class, but there's going to be another bit of reading in the notes on parallel algorithms. This is meant to be just an introduction to the idea of parallel algorithms, and just to give you a basic flavor for what it is about. So I'll ask you to take a look at this. So just give it a read, and if you understand the main ideas, I'll be asking you a very basic question on the exam about it. So just one very basic question about it. But anyways, with that being said, why don't we get started? So last day, we talked about the 0-1 knapsack problem. We seen and proved that the 0-1 knapsack problem has and satisfies the principle of optimality, which we lovingly called poo. So now what I want to do is use the principle of optimality to derive a recurrence relation that represents the algorithm that we're going to have at hand for computing the optimal value of a solution. So what I'm going to do for the sake of our convenience, because notice in our proof that we did for the principle of optimality, I didn't really care at all the ordering of the items. I just had like an item lambda, and it didn't matter what order I took lambda in that proof. So for simplicity, I'm just going to presume that their items are denoted as 1 to n. So the items will be 1, 2, 3, 4, 5, 6, all the way up to n. And each item will have profit and a weight that'll be indexed by 1 to n. This is in contrast to being indexed by 0 to n minus 1. So here's how I'm going to formulate this. And I want to convince you that the principle of optimality is what actually gave me how I did this. So I'm going to let val I wt, wt is just a variable. So it's just a name for a variable. It's not a product. I wt be the max profit by considering the first I items with capacity wt. So when I mean capacity, I'm talking about the knapsack capacity. So that means that if, for example, I consider when this is 2 and I make that a 3, this will be the value of the maximum profit by considering the first 2 items with the capacity that I had mentioned. So you can think of it like a way I'm decomposing what my instance might look like by only considering a certain number of items and considering the knapsack capacity of a given size. So this is going to help me formulate the recurrence relation that falls out of the proof I gave you last day, or at least the sketch of the proof. So recall, of course, that if I'm trying to maximize, I would like to, if I have the option to take a better answer versus one that maybe isn't as good, I'm always going to want to take the one that's bigger, right? So just keep that in the back of your mind. Just put it, like, take a feather, just put it in the back here. Wear a pretty cool hat. But there's really kind of two possibilities here for what happens when I give you a given I. So the first possibility is I don't include I. So if I don't include I, what I'm saying is the best answer for this, the max profit, was simply when I didn't consider item I, but I considered all the other items. So they may or may not be in the knapsack. But the point is that it's after I've considered the first I minus 1 items as opposed to the first I items, I'm able to tell you that the optimal profit is in fact just going to be that where I don't include it. So this is just representing where I don't include item I. The other possibility is that, and this comes actually out of the proof I gave you the other day. Remember when I did the copy and paste or cut and paste proof where I took out one item and then I injected it back in? So this is me taking out an item, then I injected the item. So when I did this, I considered a sub-instance where the knapsack capacity was decreased by that given item's weight, meaning that I have less space for more items in my knapsack. So then I just introduce in the item that I'm going to include. So you have two possibilities here. And this falls out of the principle of optimality. So are there any questions about where these two came from, just before I proceed? So all this is saying, the first one is just saying, hey, look, if I have a better answer, maybe I'll just take the first I-1 items, and after I consider those, I'll take whatever that is. I don't know which items specifically were taken, but I know I have a better value there potentially. Or I'm going to take it where I add in item I. That will decrease the knapsack's capacity by WI. So that will increase our profit because I put it in the knapsack. So this comes out of the proof I showed you the other day. This one part right here. So you might ask, okay, so how are you going to formulate a recurrence that represents the computation of the optimal solution? Well, I now have all the bits and pieces I need. So whenever I have an item with a given weight that's too big to fit into it, I know right away I'm only going to consider the first I-1 items. I would not put in item I, because item I's weight is too big. Otherwise, just as I said, if I can fit the item in, I'll take the better of two possibilities. Either I take where I consider the first I-1 items, or I take it and I take that shot where I put in the item I increase my profit potentially, and I decrease the knapsack's capacity. So in our algorithm, when we come and tabulate all of this up, these are going to end up actually being two specific spots in a table. So just keep that in mind. Now, this is naturally a recurrence relation. So this is actually representing the max profit. So notice I have a way of computing the optimal profit. But I need some base cases. So when I don't put any items into the knapsack, there's two possibilities. Either I consider none of the items and I have some knapsack capacity, right? If I consider none of the items, then most certainly the max profit is 0 because I didn't put any of them in. Or it's that I have a knapsack capacity of 0, meaning that none of the items can fit. So that means that the optimal profit in this case would be 0. So notice the ranges here. So you might ask, Dan, how are we going to use this? So how are we going to use this? Now, you remember how I talked about with our Fibonacci example, how I used parts of my pre-computed values to build up, bottom up, my solution. I'm going to do the same idea here. Nothing strange is going on. I'm just simply going to do the same idea. Except now I'm going to do it over a 2-dimensional array instead of just a 1-dimensional array. So here's an idea. I'm going to compute val as a table. I'm going to do it top to bottom, left to right. And I can compute val 0, 0, val 0, 1, val 0, w. Keep in mind, all of these ones in this row are all 0, right? Likewise, I can compute the next row, for instance. But notice that the first column and the first row are all zeros. So notice that once I have these two in place, I can try to fill in the rest of the table. Now, I have a question for you based on the definition of val over there. If I have this table that represents these values, which one has the optimal profit for my instance? So just look at what I wrote up here for val. So it considers the first I items with capacity WT. So which one here? Is it val 0, 0? Is it val n 0? Is it val 1, 1? Which one is it? Which one has the optimal knapsack profit in it? So notice I'm just computing the value of it right now. So any ideas? So suppose, just to give you an idea, well, let's plug in what we need here. So I have n items, each one with a profit or weight index 1 to n, right? So if I put n right here, that means that that is the max profit by considering the first n items, right? So we know it's in this row right here. Which column is it in? Which one has the max profit in it? Which one? So just to give you a heads up, so one dimension of this table going across goes up to W, capital W, the knapsack capacity. The other one goes up to N. Which entry in this table will have it? So we know if I consider first N items, we're okay. But what does this have to be? What's WT have to be? What's it have to be? So remember the problem's formulation? We have the knapsack capacity, capital W. So if I just compute this recurrence by building it up, by filling in the first row and the first column with zeros, I can conceivably build this top to bottom, left to right. But the optimal profit of the knapsack is in the bottom right corner. It's right in the bottom right corner. This is because of the way I formulated val here. So its val is saying it's the max profit by considering the first N items with knapsack capacity capital W. So here's the recipe for the algorithm now. Now, what I'll have to do is build this table, and I read off the bottom right corner, the last position in there. And that's how I can compute the optimal profit. So, you might ask, Dan, you gave me a recurrence relation, right? Could I turn this into a recursive algorithm? The answer is yes. You could design a divide and conquer algorithm that uses this exact recurrence relation. And here's the perk. Here's the perk. If you use memoization, then you can speed up the recursive algorithm. So instead, you'll just have a table that looks much more like this instead. Instead of just being one-dimensional array. But let's focus on the dynamic programming aspect of this. So I want to show you what this algorithm will look like. So before I do that, are there any questions? Any questions at all? I'll tell you up front, the algorithm is really nice and simple. It'll just look like I'm filling in a two-dimensional array. But the underlying theory behind it is all based on the principle of optimality. Okay, so let's head over there. Let's go over here. So let's take a look at the pseudocode for how, so remember, all I have to do is compute this table and I'll know which spot has the optimal profit in it. That's just from the definition I have here. But at the same time, I'm just using the recurrence relation. So all I'm going to do is reformulate the recurrence relation as a sequence of if-else statements inside of a loop. So here we go. So I have the knapsack for our knapsack DP here. For its input, it has an array with weights 1 to n. It has an array 1 to n of profits. And the array has length n with knapsack capacity capital W. So the first step, as I mentioned, you're going to build a table. The dimensions of this table are actually W plus 1 for the number of columns, n plus 1 for the number of rows. So here's the table right here. So I'm going to build a new two-dimensional array with these parameters. You might ask, why the plus ones? It's because of the base cases of the recurrence relation. Remember, I fill in the zeros. Now, if you want to optimize this further, you could always get rid of the first row and first column. Just hard code in that you access whenever you have to access the 0 column or 0 row. You could just make it so it just gives back 0. So if you really need to cut down space, that's one thing you can do. So that's the first thing I'm going to do. Next, I'm going to fill in the first row and the first column. So this will fill in the first row. This will fill in the first column. So those will be filling in the zeros in the first row and then the first column. Then all I'm doing is applying the recurrence relation bottom up. So now I have some initial entries in the table. And all I do is I fill this top to bottom, left to right. So notice I go for I is assigned 1 to n. For j is 1 to capital W. So I'm going to go across the row. Then I'm going to go down each one of the rows. So all I have to do is I just simply check based on my recurrence over here. Is the capacity that I'm considering, is it big enough that I could fit the item I in? And if I were to try to put this item in, would it be better than not having it in? If that is the case, then we just simply update val ij to just simply being this new profit. So that's just simply where I look up one row above me and I go left by W sub I many entries. And then I just add the profit. So you're going to see when we do the example, it's going to fill in the table, but there's going to be two specific spots we'll always look at when we actually fill in the table. So here we put the item in. Otherwise, we can't fit it in. So I just simply take the entry that's in the row directly above it. So that just means I don't put item I in. That's it. And then lastly, if I were to return the optimal profit, I just return the bottom right coordinate or position of the table. So that will contain the optimal profit. So we'll come back to the time complexity in a moment, but I thought it would be important that we do an example. But are there any questions about this pseudocode before I get too far ahead of myself? So just remember that this is a bottom-up process. So I'm going to start off by filling in the base cases in the table. So think of it as the recurrence relations base cases. I fill those in, and then I'm going to fill in the table in the order that is prescribed by these loops. So you're going to just see I'm just going to fill in the table. That's all the algorithm is going to do after this point. Okay. Should be 2 thumbs up if we're all good. I just want to make sure we're all on the same page here. Okay. No, good. No, wonderful. So let's proceed. So this is neat. So we can use dynamic programming to even tackle problems that are a little tougher. So one remark I do want to make while I'm erasing this board over here is that Zero and Knapsack, we presently do not know how to design a polynomial time algorithm for this problem for Zero and Knapsack. So to expect this algorithm to run in polynomial time might be a little suspect. But I'll tell you this is one of the better known algorithms for this problem. It's especially the case if you know that the knapsack capacity is a constant. So let's have some fun here. So here we go. Let's do an example. So let's do this one. We're going to have 5 items. 1, 2, 3, 4, 5. So I'm going to have 5 items. We're going to have weights. And we're going to have profits. So the weights are going to be 6, 5, 4, 2, 2. The profits are going to be 6, 3, 5, 4, 6. And we're going to have it work. So we know n is 5. Capital W is going to be 10. So the knapsack capacity is 10. So remember that we have arrays here. So these are going to be indexed from 1. Because I have 5 items, it'd be from 1 to 5. So just keep that in mind. It's a one small little implementation tweak that I have made. And that was a cat. if you heard a meow. Anyways, let's do what the algorithm tells us to do. So anyways, sorry, I just lost it. So remember, in the algorithm, we first do what? What is the first thing we do? Somebody tell me. So what's the first thing we do? Yeah, I create the table, right? So let's build the table. We know the dimensions of this table. So you notice that capital W is 10, so you know you're going to have 11 columns. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how many rows am I going to have? I'm going to have 6 because I started 0. It goes 0, 1, 2, 3, 4, 5. Notice the extra dimension, one extra on the rows and columns. So the algorithm tells me I'm supposed to fill in the first row and first column with zeros. So that's the first 2 loops. I just fill those in. So that's the first thing I do, right? I just go through those 2 loops, I fill in the zeros. Piece of cake so far, right? So let's start looking and try to compute these values. So before we get too ahead of ourselves, I just want to remind you that this is heavily based on it's based on the recurrence relation, right? So every time I do this, I have to appeal to if the item fits in the knapsack. And this will correspond to the column, by the way. So notice that our WT in the recurrence relation is actually the column. So for example, when I look at 4 here, this will represent knapsacks where their capacity is 4. Likewise, if I look at a given row, like if I look at 2 here, this is what I consider the first 2 items. So I would consider 1 and 2 here, for example. So just keep that in mind as we do this. So I look at item 1. Notice its weight is 6. So we know that it will not fit in a knapsack up until this point, because the knapsack capacity needs to be at least 6, otherwise it's not going to fit. So I'm just going to start off doing something a little bit basic, just based on our intuition here. But we're going to start seeing that we're going to actually need to compute this recurrence relation a little bit more carefully. So in this case, my choices are, so for this one, I can fit in item 1, so I can still fit in item 1. I haven't considered the other items yet, so you know right away that the rest of this is just going to be 6s. So if you ever want to check that this is indeed the case, well, you can compare the max of these 2 things. So if I look at this entry, I look directly above it, I have 0. So my choices are, okay, I take the 1 directly above me, or I check, okay, so what's 6? So if I take column 6 and I subtract off the weight of 6, it'll get me over here, and it says, okay, add its profit, which is right there. So that's why I put a 6 right there. So there's kind of two entries that are your best friends. The one directly above it, and the one in the previous row, so the one just above it, minus whatever the weight is of that item. So in this case, you would be looking at 6 minus 6, which is 0. So those are our 2 best friends when we're filling this table in. So that will change based on which item I'm considering. So in the second row here, I'll be considering when I can include item I in or I don't include item I in. So we know right away that we cannot place item 2 in until the weight of the capacity of the knapsack is at least 5. So I know right away I could just go. So you know right away I could get a profit of 3 right here. So you might say, Dan, what's going to happen next? So in this entry here, I have 2 choices. I either take the one directly above me. So I have 6 versus I go up 1 row. I subtract off the weight of that item. So 6 minus 5 is 1. So I have 0 plus, so be putting the item in is 3 for its profit. That's most certainly the case that it will be that 6 beats 3, so I'm going to put 6 right here. So I just take the one directly above it in the table. And this will be true for all the rest of these, because notice the knapsack capacity is 10 at most. And I know that my weights of these 2, if I sum up their weights, it's 11. So if you ever find yourself just wondering, what do I put in? Always appeal to the recurrence relation. But really, the intuition is very conceptually simple. Either I consider the first I minus 1 items, or I consider when I put in item I, can I get a better profit? So as long as you can remember those 2 cases, you can fill in this table like a piece of cake. So let's do another row. Let's go a little bit further here, because it's not going to get very interesting until we get really far down. So I have row 3. So I know that item 3 has weight 4, so I know I can't put an item 3 until I'm right about here. So my choices in this case, so now I have something interesting going on. Either I take the one directly above it, or I take the entry in the row directly above it, minus off the weight of that item. So in this case, I have item 3, which is, its weight is 4. So I take 5 minus 4, which is just 1. So I have 0 plus the item I would put in, which in this case, it's 5, right? So it means I have 3 versus 5. I'm going to take the 5. Then let's keep going. Let's keep going. So you're going to notice very quickly that we're not going to have anything interesting happen for these next few entries because it's 6 versus 5. Because notice that the knapsack capacity needs to be at least, in this case, I think it has to get closer up to 9 or 10 before anything gets really interesting. But let's just check. So I have 6 versus, okay, so we got the weight of item 3, which is 4. So 6 minus 4, which is 2. So I have 0 plus 5 versus 6. So I take the 6. This will be true for this one as well. This will be true for, I believe, this one as well. But now this is where it gets interesting. So I have 6 versus, if I have the weight there, 4. So I have 9 minus 4, which is 5. So I have 3 plus 5, which is 8, which is bigger than 6. And naturally, you can fill in the next one, which would be 11. So are there any questions so far? So all I need to do is consider 2 cases. That's it. I look at the one directly above me, or I look in the column of the row directly above me. I look at that number, and I add the profit of my item. And I see which one's bigger. So for the sake of time, I'm just going to fill in the rest here until we get to near the end. So I have 0, 0, 4, 5, 5, 9, 9, 10, 10, 11. This bottom row, I have 0, 0, 6, 6, 10, 10, 11, 11, 15, 15. Let's fill in the last one together. So my choices are either 11, and I'm considering item 5, right? So it's 2, its weight is 2. So I have my choices either 11, so it's 11, versus, okay, so we're at column 10. So 10 minus 2 is 8. So I have 10, plus the profit of my item is 6, so I get 16, which is better than 11. So I have 11 versus 16, I get 16. And now, if I want to know what the optimal profit is, it's 16. So 16 is the optimal profit. This would be what the algorithm I gave you over here will return. Now, you might say, Dad, you told me how to get the value of it. How do I actually get the solution itself? Like, how do I know which items to pick, right? Remember, that was one of the big things we had, was we formulated as we give a vector with all of our x values, right? So it's either going to be 0 or 1 here. So you might ask, Dad, how do you do this? And it all comes back to how we formulated the, say it with me, principle of optimality, or lovingly we call it poo. At least in this class. So anyways, so you might ask, Dad, how do we determine which items we take? So there's actually a backtracing process that we use. So it's often called backtracing. Not to be confused with backtracking. These are 2 different things. So what we're going to do is I'm going to show you how you can navigate through this table and find out all of the choices of the items. So believe it or not, what we've encoded in this table actually tells us all of the decisions that happened. This is one of the, I don't like to use the word magic, but this is one of the magical, like I'm thinking like in the most whimsical way possible. This is one of the magical things about dynamic programming, is not only does it give you the profit, like our optimal answer, but it also tells you how those process or decisions have been made, because that's how we formulated the recurrence relation. So remember, there's 2 cases. Can anybody remember what those 2 cases were? So either I put the item in or I don't put the item in, right? Those are the 2 things I had. So let's talk about how we actually get the items then. So let's think about this. So when did I not put an item in, by the way? Does anybody remember what I did in this table as I was filling them in? What I did whenever I didn't put an item in? What did I do? Can somebody tell me? What did I do when I filled this table in when I didn't put the item in? Yes, so what we had happen, so what we did when we picked the item, we always went up one row, and then we went and shifted by the weight of the item, and we seen if we could get a bigger number by adding it in, right? But if I don't put it in, I just looked at the direct entry above me, and I copied that value down, right? So there's really just two possibilities that can happen here. So if you remember that, that's all you need to know how to carry out this backtracing process. So I'll have the details for this, so some pseudocode for this in the notes. But I want to make sure you know recognize these two cases. So you're just going to start in the bottom right corner. So we know that we take an item when these numbers don't match, for example. Why? Because I didn't copy that value over, right? So if val ij is not equal to val I minus 1j, what does this mean? We include item I, right? Likewise, if they're equal, so if I have the same thing where they're equal, it means I do not include it, right? But what did I do when I picked the item, right? I always went to the appropriate column by subtracting off the weight of that item, right? That's what we're going to do here. So if we include this, what we're going to do is we're going to move left by wi. So we're going to move left by this amount, but regardless, when I do this process, I'm going to always move up the table. So I have these two possibilities, so these two cases. What's going to happen is I'm just going to work my way up the table row by row, and whenever I pick the item, I'm going to shift to the left by the number of columns that would be represented by its weight. Whenever they're equal, I'm just going to go up one row. So we're going to see how this plays out. So this is a rather crafty process, and many, many dynamic programming algorithms are about as natural as this. So if you just realize this process, let's see. So we know right away that 11 and 16 don't match each other, right? So I'm going to include item 5 in here. So we know item 5 is definitely going in the optimal solution. So what do I do? Do I go up? Yeah, I go up regardless, right? So I'm going to go up. I'm going to draw some arrows. This often is very helpful to see what's going on. I'm going to go up one row. Then I'm going to decrement off the weight of item 5. So I'm going to go left by 2. So I have 10 minus 2, which is 8. So I go up, then left. And now I look, 10 versus 6. These are not the same, right? So I'm going to take item 4. So I go up one row, regardless. And then I decrement off the weight of item 4, which is just 2. So 8 minus 2 is 6. So now I'm right here in the table. Then I have 6 versus 6. Should I put in item 3? Should I put in item 3? So notice that maybe I shouldn't put in item 3, right? Because look, this matches this. So that means that we shouldn't put in that item. So it means we're going to just go up one row. These two are equal to each other, so I'm going to go up one row. These two are not equal to each other. So that means I'm going to take this item. So I'm going to take item 1, because that's what row we're in, row 1. And now all I do is I go up one row now, and then I decrement off the weight of item 1, which is 6. and now I end the process because I'm in either the first row or first column. That means I am now done. So you just keep doing this process until either I or J, if you think of I and J like positions as I'm going up and down, sorry, up and left in this process, when I hit the first row or first column, you know you're done because there's no way you're gonna, remember, this first row doesn't represent an item, right? It means there's no items that we have left to consider. So are there any questions about this process? So I have all the details in the notes if you want to see some pseudocode for this, but you can very efficiently implement this algorithm just using a loop. So this is what we often refer to as the backtracing process. So we can use this backtracing through the table using the recurrence relations definition to tell me how to get the actual optimal solution. So I must stress that this does not add any additional time complexity to the overall algorithm that I gave over there. It'll just be an extra step. So rather than returning the profit there, you just have this backtracing process you go through. So are there any questions about how I filled this table in or this backtracing process? So you'll find that this is one of the beautiful things I like about dynamic programming is this backtracing process. So it lays out, by the way we filled the table, all of the decisions we made along the way. So if we're okay, give me 2 thumbs up. I want to know if we're doing good. Excellent, excellent. Very good. So let's talk about the time complexity now, because that's actually one of the interesting things about this algorithm. It's actually very different than a lot of the algorithms I've shown you up to this point. And it's not it's not necessarily unique to dynamic programming. It's more unique to the kinds of problems that we're looking at. So do you remember back near the beginning of the course? I think this is like right near the beginning of this whole class. You remember how I talked about that there's these problems that have numbers in them? Do you remember me talking about this when I talked about input size? How I talked about there's problems that they involve numbers. So I have to sometimes be very careful about how numbers occur with respect to the running time. So I want you to keep this in the back of your mind as we try to do the time complexity analysis here. So here's the great thing. This algorithm is really simple to analyze. So let's kind of walk through this. So to create this table, well, I could do this in big O of NW, right? Next, I go through these. Each one of these is done by some dimension. So it's just simply okay, these here are big O or big theta. We'll say big theta for simplicity purposes. So this is big theta of W because I go across the columns. This one I go across the rows. And then I have this nested loop. And here's the great part. Everything you know about counting rules apply right here. So notice that I go from I is 1 to N, J is 1 to W. And I like to show this example towards the end of the class just to show you how far along you've come with the way we've seen things in this class. So we know what the time complexity of this nested loop is, right? Can somebody tell me what it is? So how many operations are happening with this nested loop? I'll tell you, it's very simple. It's very simple. I like to show this one because it's surprisingly simple. So what should I put? Oh, yep, NW. Very good. So it's big theta of NW. So what does that mean? That means the worst case time complexity, or I'll just abbreviate as time complexity of this algorithm, is big theta of NW. We're capital W there. That is the knapsack capacity. So you might say, Dan, that's wonderful. That's wonderful. It looks something like a quadratic, or even it looks something like a quadratic, right? Like it's n times a something, which usually you might say, okay, that looks like some product, right? It's one thing that we're used to doing, right? It looks something kind of like a quadratic because there's a product of 2 parameters in our problem. But here's a big but. If I told you what that looked like, what kind of function would that look like? Just ignore the fact that we're not talking about the input size. Just tell me what that looks like. So we have a name for this. Starts with a P. It looks like something. It doesn't have to be, but it looks like it. It's something only, sorry, I was having a little bit of fun there. Yeah, polynomial, exactly. It looks like a polynomial, right? So notice that this looks like a polynomial. It looks like a polynomial, right? You'd think that would be first thing you'd think of. She's like, okay, Dad, that's a nice polynomial running time. But there's a little wrinkle in this idea that we're missing here. There's a little thing that we've omitted when I say that. It's a very important one for when we analyze the algorithms. The question is it actually a polynomial or not? In the sense that we talk about our input size. So I like to show this example because this is by the way, if you're thinking back to beginning of class, I promised you I was going to show you an example like this. So this exhibits actually a very strange phenomenon. So this is kind of strange, right? So all terms of the running time and I'll put in quotation marks, are polynomial. But, this is the big but. Not all the terms are polynomial with respect to the input size. There's that thing we talked about, the input size, right? That's how we normally characterize our discussions around complexity, right? So, we have actually a special name for what we've run into. So, running times that look like this are what we call pseudopolynomial. So if you're wondering what pseudopolynomial means, so pseudopolynomial time is as follows. So I'll just say an algorithm is said to run in pseudopolynomial time if its running time is polynomial with respect to the input size when the numeric part of the input is encoded in unary. So here's that thing I was telling you about at the beginning of this class. So I want to write out what the running time is here. Remember, it's NW like this. What is capital W? Can somebody tell me what capital W is? It seems to be rather suspicious. Like, is it, like, what's its type? Like, what's the type of capital W? What's its type? You think of it like a data type. So we know that there are n items, right? But what about capital W? We know this is the knapsack capacity, but what is the knapsack capacity? Like, what is it? Like, what is it? It's an integer. It's an integer. So when it appears in the running time like this gets rather peculiar, especially that we're dealing with a problem that involves numbers. You might ask, why? Why is our algorithm Why does it run in pseudopolynomial time? It's really because W is not a constant, right? It's not a constant. It is represented with, I'm just going to give a name for a variable, k is equal to big O of log base 2 of W bits. So you might ask, Dan, why is that a big deal? Remember, the input size of W, the number of bits required, is big O of log base 2 of W. Yeah, big O like that. So keep in mind that W could be much bigger than the integer sizes of the items that are in it. So remember, our instances consist of a whole bunch of items that have profits and weights. W is unrestricted by this completely. W can be much bigger than the integer values of the items for their profits and weights. That fact alone is actually a very interesting one from a theoretical standpoint that I won't be able to talk about here. If you're curious about it, let me know. Let me know obviously after class. But so if you think about this, when I write capital W like this, and the input size of W is big O of log base 2 of W, what does that mean with respect to when you see W like that? So if I have a logarithm of a something versus the something, how much bigger is W versus log base 2 of W? Are they like linearly roughly the same scale or proportion? Or is it much more? It's actually, if you think about it, yeah, it's exponential, exactly, very good, very good. So notice that, so this means W is exponential with respect to the input size. Because of this fact, right? So in fact, you could easily replace this capital W with 2 to the power of k. So even though it looks like a polynomial, you can actually rewrite it as an exponential time algorithm. So sometimes you run into these kinds of algorithms. A lot of them use dynamic programming. And when you have pseudopolynomial time algorithms, sometimes they lead to interesting theoretical consequences down the line. In a class beyond this one, I would normally talk about something like this. But I will tell you up front, the algorithm I gave you, with some simple tweaks to it, we can actually design an algorithm that could give you an answer, always within, say, 1% close to the optimal answer in polynomial time. Now, I want to talk briefly about polynomial time. Like, how can somebody make any suggestions on how I could make this algorithm run in polynomial time? What special case is a very natural one to make it so that this runs in polynomial time? So you know right here that I said W is not a constant. So maybe if W is a constant, this indeed runs in polynomial time, right? So in practice, if W is small, you can actually come up with a polynomial time algorithm. But remember, that's not the 0 on knapsack problem. That's a special case of it. So anyways, are there any questions about this discussion about pseudopolynomial? So this is a very interesting phenomenon that some researchers study, for example, in the areas of approximation algorithms. And it's a rather interesting and kind of deep rabbit hole you could go into, where the existence of these kinds of algorithms leads you to come up with nice approximation algorithms. But beware, not every dynamic programming algorithm will lead to a pseudopolynomial running time. The longest common subsequence example I want you to read in the notes. So make sure you take a look at that. I'll ask you a basic question about it. In this one, the running time is not pseudopolynomial. So, are there any other questions before we talk about a new topic? So you might find this longest common subsequence example interesting, especially if you are interested in things like bioinformatics or even string-based problems. So if we're okay, let's move on to a brand new topic. So this is going to be the final topic of the class. So I'm going to be laying down something I planted a seed about earlier on in the course. We're going to be revisiting the idea of a reduction. So we talked about reductions actually briefly when we were talking about lower bounds. But now I want to actually introduce the idea to you properly, like in a more formal sense. Because if there's one thing that I want to ensure is that even though this concept at first will look highly theoretic at first, it's actually an incredibly powerful idea that pervades a lot of theory of computation. If you take a class like CS 411 or 412, you'll probably run into this technique. It's a very powerful one, but most certainly it's one that allows us to talk about problems in a way that is beyond the things that we've talked about so far. So, for example, I could talk about different problems like, almost like, I don't want to draw this analogy, I'll give you a couple fun ones. So, for example, there's zoologists that study, for example, different animals, and they look at the relationships between those animals, for example, comparatively. But you could also think of it like, almost like Pokemon, for example. You have all your Pokemon, I want to collect them all, I need the hat. But the point is that there's relationships between the different entities. Reductions actually give us a tool to bridge these relationships, and it opens up a wide door to everything you know about problem solving. So I'm hoping that you'll find this last topic especially interesting, or at least something I want you to think about. So we're entering the final topic of this class. So we're going to talk about complexity theory. I'm going to introduce a basic notion of intractability. So up to this point, I've been talking briefly about, this problem is hard. I never really gave you a notion for this, so I have to tell you about that. And more. So we're going to be revisiting reductions. So I want to describe what a reduction is. So we're going to revisit reductions now. So, we've seen this idea before when we talked about lower bounds. I'm going to revisit it more carefully now. And we can use this to draw connections between different problems. So I'll say, we can use reductions to draw connections between problems. For example, the notion of a reduction actually can be used, say if you have an algorithm that solves a much broader class of problems, and you want to have some way of using this algorithm to solve your specialized problem, this idea of a reduction can be used to convert it to that problem of interest, and the idea behind it is that it will give you the same solution. So here's the idea. So given problems, capital Pi 1 and capital Pi 2, a reduction, so I'll define it as a function. A reduction f is going to take instances of Pi 1 and it outputs instances of Pi 2. So you might ask what f is. The technical term for this is a computable function. But for those that just want to have fun with this stuff, you might just say that this is some algorithm that runs in finite time. So we talk more about computable functions, for example, in CS 411. But in the idea is that I have some function that's going to take and transform instances of Pi 1 into instances of Pi 2. So this f is a computable function. Just think of it as just an algorithm. So what it does is, as input, it takes Pi 1 and then it spits out an instance of Pi 2. You can think of it as transforming it or constructing that. So where where f transforms any instance x among pi 1 to an instance of pi 2. So at first this will seem a little bit, I don't know, it sounds a little bit like, Dad, you're making up some fun stuff, but it's actually a very natural idea. I want to draw a picture in the moment, but I just want to make sure you have the other bit of this, is that instance f of x, which this is the instance of pi 2, has the same answer. I'll put air quotes around answer as x. We say that pi 1 reduces to pi 2. So you might ask, Dad, what does that mean? So this is a technical phrase, by the way. If ever you find yourself picking up a paper about complexity, they'll use very often this phrase, or they'll say pi 2 reduces from pi 1, as opposed to 2. So you might say, Dad, what does this mean? Like, what is this f and all this stuff? You say it has the same answer. What does it mean? This is the high-level way I like to think about it, and I hope that you might find this another way that might be helpful for you. Another way to think about it is pi 1 can be solved in terms of pi 2. It can be solved in terms of pi 2, as pi 1 is at least as easy as pi 2. So one natural way you can think about these reductions is like I'm able to transcribe the problem into a different language that describes a different problem. So sometimes these are breakthroughs in developing better algorithms sometimes. Other times it's just a natural relationship that two problems actually have. So where you have one problem, actually you could rewrite that problem in terms of a different problem, but as a special case of it. So if you have a nice algorithm for pi 2, then you could just use pi 2 if you could translate whatever pi 1 is in terms of pi 2. That's the point of a reduction. That's one way you can think of it. So that means that pi 1 has to be at least as easy as pi 2 because I have some way to solve. This means that there's some way to turn them into instances of pi 2. So it means if I can solve pi 2 very fast, that means I can solve pi 1 really fast. But on the opposing side, here's the other part of this that's rather powerful. Or that pi 2 is at least as hard. As pi 1. That's another way you could view the same thing. And that view is a rather important one if you take a class like CS411, where we might want to learn about, okay, this problem is at least as hard as this other problem, and what if it is the case we don't even have algorithms that solve a certain problem? I know, mind blown. It's kind of weird. So let's talk about this. I'm going to draw a fun picture. So it's easy for you to just write this formally. I should draw you a picture, and I'm hoping that this will help make this a little bit more concrete. So this is something you can easily translate into something for practice. But most certainly it's not just a theoretical tool, it's also something you could do to solve multiple problems, just translating them into other terms of problems, but doing it hopefully efficiently. Notice that in my definition, I didn't require that the algorithm actually is efficient, right? It just has to be some algorithm. So here's a picture. So this might remind you of a picture I drew the other day. Well, a while back. So suppose I have an instance of pi1, and I want to solve pi1. Like, I want to be able to solve pi1. That means for every instance of pi1, there has to be some algorithm that I can use to compute its solution, right? So here's an idea for how I can do this. So here's my algorithm for pi1. So first, I'm going to give this to the algorithm. It's going to apply this reduction f. So remember, the reduction f is just an algorithm. You're going to see some examples of this either today or next class. Probably next class. As a result, I get f of x, which is going to be an instance of pi2. Then I can just give this to the algorithm for pi2. So this seems like a really nice idea, but here's the key part about the reduction, is that when I get the solution from this, so if I get the solution for f of x, which is in pi2, it has to be that the solution for this gives me the solution for the original one. So it gives me the solution for x. So they have the same answer. So the way we might describe this can be done a little bit more precisely. But in the context of what we're going to talk about here, we're going to talk about so-called decision problems in a little bit, where when I say an answer, it's either going to be a yes or a no. So meaning that if I get a yes answer over there, it has to be that a yes answer comes out here. I'll give you another example of something that is very real. Recall that, I must claim that this is not the fastest way of doing this. I just want to make sure it's clear. So suppose that I want to compute the shortest path tree for an unweighted graph. Suppose that that's pi1. One thing I could do is I can always take that graph, I can make it into a weighted graph, where all of its edge weights are the exact same numbers. So they might be some constant c, or just one. One works well enough. As a result of this, I end up with a weighted graph. And I have a question for you. If I wanted to compute the shortest path tree of a weighted graph, can somebody tell me an algorithm I could use? Tell me an algorithm you could use to solve that problem. So, computing the shortest path tree of a weighted graph. So, in particular, in the setup that we had in class. Not prim. There's another one. Dijkstra. Yes, Dijkstra. So you could just use Dijkstra's algorithm. It'll give you the shortest path tree for this instance, which obviously if you just ignore the edge weights, you get the solution for this instance, right? So do you see how you could use this idea of a reduction to convert one problem into another problem? So you could use this reduction idea to translate a problem into a different problem. Now this example is rather straightforward. We're going to see a little bit more of a complicated example in a little bit. Probably next class, we'll see. But the idea is that these have the same answer. That's really the key of this. So that's what makes the reduction work. So the idea is I apply the reduction, but here's the idea. The idea is rather straightforward, is that I have my reduction, and it gives me the recipe, if I have an algorithm for pi2, to solve pi1. But I must stress that this relationship isn't symmetric. It's not symmetric at all. Possibly, for some problems it might be, some problems it may not be. Notice that this doesn't give you a general recipe to convert each instance of pi2 into pi1. So notice that it's only one directional, this reduction. So notice that it converts pi1 instances into pi2 instances. It doesn't do the other way around. That's why I said in my example that all of my weighted graph examples all had edge weights of 1, which matches what I wanted to formulate over here based on my reduction. And the key idea here is that the reduction tells me how I know they are the same answer. So here we go. here's the consequences of this. Here's some consequences that I just want to make sure I spell out that are really important for us. Consequences. If pi 1 reduces to pi 2, and pi 2 is solvable as per what we've talked about, is solvable, then pi 1 is solvable. Now I have a question for you. For those that are thinking about this logically speaking, what does this also mean if I just flip it logically? So I gave a hint about it earlier on. So if I know that I have an algorithm that solves that problem, then I know pi 1 is solvable. What about if I flip this around? This is the one that's a little bit more interesting in my opinion. If pi 1 reduces to pi 2 and pi 1 is unsolvable, then pi 2 is not solvable, right? It's a little bit interesting, right? Like, oh yeah, the reduction actually gives you a recipe. So if you know that pi 1 is unsolvable, all you do is if you can translate it to instances of pi 2, then you can say pi 2 is also unsolvable. Because you can think of pi 1 as almost, it's intuitively speaking, it's like a special case of pi 2. Just I have to translate it in terms of the language of pi 2. So that's really interesting, right? Like, so now we actually have a tool to tell us whether there exist algorithms or not for certain problems. That's a little funky, right? So anyways, I want to talk briefly about decision problems, because it's important that we know how I'm going to be framing these reductions for this section. So the idea of a reduction itself is very useful, not necessarily within the context of decision problems, but most certainly you can study reductions still with optimization problems. But in the context of this, it's easy enough for me to talk about decision problems, which I'm going to define in a moment. So I'll say we will focus on decision problems. You might say, Dan, that's rather restrictive, right? It's just yes and no answers. But believe it or not, many problems can be easily recast as decision problems, which I'll give you an example in a moment. So that means, so you might ask, what's a decision problem? So it means that instances can be formed where they have either yes answers, either yes or no answers. So you remember the picture I showed you at the beginning of the course, right? Where I have my problem instances, I have a solution. Here the solution is a yes or a no. That's all I'm saying. So I'll refer to the instances that have yes answers as their solution as yes instances, and the ones that have no answers for their answer, their solution, those are called no instances. So this will be very helpful for us because what we would like to do is have some way of transcribing which ones are the yes answers versus the no answers. So I want to show you how a reduction would be pictorially seen as a decision problem. So if I have two decision problems, so here's pi 1. So just imagine my picture I have over there. These are all the instances of pi 1. I cut it down the middle. I don't necessarily know if it actually would be about the middle, but there's going to be yes or no instances. The idea is that the reduction, remember, it has to produce the same answer. So for pi 2, it has to be that whenever I have a yes answer, no answer, every one of the yes answers have to translate to some subset of the instances of the yes answers for pi 2. All the ones that are no instances have to translate to some subset of instances that are no instances for pi 2. Why? Because if I gave you an algorithm that solves pi 2, if you look at my picture here, if I solved the instance that I transcribed it over to this one, a yes answer would mean a yes answer, right? And a no answer would mean a no answer. See, isn't it nice? So let me give you a quick example just to distinguish between a decision problem and an optimization problem. Let's consider a minimum spanning tree. So I'll just say many problems can be formulated as decision problems. So you can think of the minimum spanning tree problem as an optimization problem or as a decision problem. So we'll think about the minimum spanning tree problem. So there's the optimization version, right? This is where you have to give it a weighted connected graph G, compute its minimum spanning tree, right? So in this case, we're given our graph G, and we have to compute the minimum spanning tree, right? That's what we do in the optimization version of this problem. In the decision version of this problem, here's how you could actually represent the same idea. So given a weighted connected graph, graph G is equal to VE, and an integer K, does G have a spanning tree with total cost or total weight at most K? So notice I framed it as a question. So I could reframe the minimum spanning tree problem as a decision problem, where if I give you the graph, I want to know if the graph G has a spanning tree with total cost at most K. The answer is either yes or no. Now, just for the sake of brevity for today, one thing I could note is that you can always modify binary search to simply address this question over and over again until you find the smallest value for K. You can actually solve the optimization version of this problem if you keep around the tree that you're computing. It's a very natural thing to think about. Many optimization problems can be translated just like this. So I want to say one last thing before we stop for today. I want to talk briefly about an unsolvable problem, because it's important that I tell you that there do exist computational problems that are unsolvable. So I mean, like, in the most literal sense, unsolvable. I think it's a perfect place for me to stop if I tell you a little bit about this. So just be aware that there do exist computational problems that don't have algorithms for them, at least under certain theses that we talk about more in 411. So an unsolvable problem. So here's an example of an unsolvable problem. Here's the input. An arbitrary computer program C. Say this is given in some programming language. And then you might ask, okay, so what are we doing with this? Here's the output. So I have this, and I'm going to have it have some input W. So imagine it almost like the command line arguments for the program. So input W for C. So imagine this is the input for the program that you feed to it to do the processing. So the output is, does C terminate does C terminate on input W? So that's the question. Does C terminate on input W? So I give you an arbitrary input, an arbitrary computer program. Can you tell me if C terminates on input W? So for some of you, you might think of this as, oh, I'm basically making an infinite loop checker. Or even just that the program does what is expected. Does it terminate? The technical term for this is halt in the context of computability. But I will give you a little bit of background with this, but then we'll stop. So one thing I want to tell you is that Alan Turing, so you may know that name, in 1936, proved this problem is unsolvable. It's unsolvable. So if you want to learn about how you could prove this, you learned this in CS411. So this is an example of a so-called undecidability result. So we call problems that don't have decision algorithms, we call them undecidable. So-called undecidability result. So that means, and you might know actually the name of this problem. You might know it as the halting problem. You may have heard of that before. So some people call it the halting problem. So I must stress that there do exist an infinite number of these unsolvable problems. So you can't just simply enumerate in a finite way all the unsolvable problems. Unfortunately, there is an infinite class of all of these. And the natural question is, which ones are they? Well, this is the thing. If you know that this problem is undecidable, as it has no algorithm, if you use a reduction, just like the one I told you over there, you could use that to prove other problems are undecidable, meaning they don't have an algorithm that solves them. So in a course like CS411, you'll learn all about this. So I would say thank you very much. So when we come back, we'll talk more about these reductions. We'll see an example, and we'll talk about the so-called P versus NP problem. And that'll wrap things up for the course. So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.